So how to calculate the shear stress? That formula we have developed is given as tau is equal to V multiplied by Q divided by I divided by B. So we'll use this formula here to calculate the shear stress at any distance y from the neutral axis in the case of solid rectangular cross section. So let's say we have width is equal to B, we have depth equal to D. For a given rectangular cross section, this point is representing the centroid and the horizontal axis represent here the neutral axis. In this case, we can replace the value of Q as A into y bar. A into y bar is nothing but integral of y dA over the hatch area. So we'll make here one longitudinal cut through the beam at a distance equal to y1. So we'll make a cut here at a distance equal to y1. The rectangular section is considered, the width is remain constant. So we'll get here this hatch area. This hatch area is same as our FGHI. Since we are interested in the distribution of a shear stress, so we'll consider here one elemental area. Let here represent this area as an elemental area, which is equal to dA, and the width of this section is same as the width of the original rectangle, and this area is at a distance equal to y from the neutral axis, and let's say it has a thickness equal to dy. So this one is the area dA, it has a width equal to b and the thickness equal to dy, and this area from the neutral axis at a distance equal to y. So we can calculate the value of Q here. We replace the value of dA as a b into dy. So we can calculate the value of Q as integral v of y, and dA is replaced as b multiplied by dy. In this case, the value of b remain constant. It has a uniform width. This width does not change with respect to y. So we can take out here b outside. Limit of y will be y1 and the upper limit of this one will be same as d by 2. So we have lower limit in this case will be equal to y1 and the upper limit will be equal to d by 2. So in this case we have q is equal to, width can be taken outside, so we have b into integral of y into dy, and we have lower limit is y1 and the upper limit is d by 2. Integral of y is same as y square by 2, so we'll get the value of q is equal to b divided by 2. We have y square is same as d square divided by 4 minus we have y1 square. We know the value of Q, so we can calculate here the shear stress tau. So in this case, we have shear stress tau will be equal to the shear force V divided by I. At a given distance y1 from neutral axis, we have width is same as equal to B. It's a constant value multiplied by Q. Q will be equal to B divided by 2 multiplied by D square divided by 4 minus y1 square. So this width is get cancelled here, and we get a shear stress at a distance y1 is equal to V divided by 2 times of moment of inertia I multiplied by d square divided by 4 minus y1 square. So we observed here that the shear force at a given section, moment of inertia of a given section, and the depth d is remain constant. It means that we have shear stress is proportional to minus of y1 square. That is the distance of neutral axis. This is representing the parabola. So we have a shear stress distribution will vary parabolically, and we have negative parabola. It means that this parabola is going towards the left, like this one. This one is a leftward parabola. Let's consider here 2 points, one on the top fiber and one at the bottom fiber. So at top fiber we have point is equal to A, and for bottom fiber we have point is B. In this case, for both the top fiber and bottom fiber, we have y1 value will attain equal to d by 2. So we have y1 for top fiber A and B will be equal to d by 2. If I put here y1 equal to d by 2, this term will be d square by 4, and d square by 4 will get cancelled, and in this case you will get the shear stress at A as well as the shear stress at B will be equal to 0. So at this both point here, the shear stress will be equal to 0. Then we'll consider a one point which is at the neutral axis. So for point C, we have value of y1 will be equal to 0. And this value y1 is 0, it means that we have maximum value of a shear stress. So in this case, we'll get the maximum value of shear stress tau max will be V divided by 2 times of I multiplied by d square divided by 4. So we have maximum shear will be equal to V multiplied by d square divided by 8 times the moment of inertia. For rectangular cross section, we have moment of inertia is B into d cube and divide by 12. So we'll shift the 12 in numerator. Dividing numerator and denominator both by 4, we will get in the numerator 3 divided by 2. One of the d square will get cancelled and we have V divided by BD. Area of the cross section here is A is same as equal to B multiplied by D, and V is the shear force. In that case, we can calculate the average value of a shear stress as equal to the shear force divided by area, that is same as equal to V divided by the cross section area equal to BD. So this term here is same as V divided by BD is the average shear. So in the case of rectangular section, we have tau max will be equal to 3 by 2 times tau average. And our distribution is a parabola. So this one is representing the distribution of a shear stress. Exactly at the neutral axis here, we have tau is equal to tau max. And the shear stress on the top fiber and bottom fiber is 0. This is exactly opposite distribution of a bending stress. The bending stress is maximum at A and B and is 0 at a neutral axis. But that was a linear distribution and this one is a parabolic distribution. So simple objective questions they can ask you about the ratio of the maximum shear in the case of solid rectangular section to average value of a shear in a solid rectangular section. So this ratio is same as 3 by 2, that equal to 1.5. Do the same analysis in the case of triangular section, circular section, but I will give the direct formula for the triangular section and the rectangular section. One case we'll discuss in detail, that is the I section and the T section. So consider here we have a solid triangular cross section of width equal to B, depth equal to D. Because of a symmetry here, we can locate the centroid. Centroid will be at a distance equal to D by 3 from the base, and from apex the centroid at a distance equal to 2D by 3. This axis is same as the neutral axis here. So again you have to take here one fiber and you have to calculate the area, but this time the width is variable, so you have to develop the equation for width with respect to y distance. So that process is a little bit complicated, so we'll just show here the distribution of a shear stress. So if you take the apex here, then there is no area above that apex, so shear stress will be 0. Similarly, if you take the base here, below the base we don't have any area, so shear stress is 0. We are getting the distribution is something like this. So as far as the distribution is considered, we have maximum shear stress at this location. So this one is a maximum shear stress, and in the case of triangular section, this will occur at a depth equal to D by 2. So approximately this distance is same as D by 2. Then this shear stress here is the shear stress at a neutral axis. So we'll represent this tau and we have suffix is Na. The total area of the triangular section is equal to 1 by 2 base multiplied by depth. So we have 1 by 2 base multiplied by depth, and the average value of a shear, that is tau average. The average value of a shear stress is the shear force divided by area. Once we know the average shear stress, then we can calculate the value of tau max. This value of tau max will be same as equal to 3 by 2 of tau average. And the shear stress at a neutral axis is equal to 4 by 3. 4 by 3 is 1.33 and 3 by 2 is 1.5. So we have maximum shear equal to 1.5. And the shear stress at a neutral axis is 4 by 3 of tau average. And how to calculate tau average? Tau average we can calculate as V by A. Now consider the case of a solid cylinder. In this case we have diameter equal to D. We can comfortably locate the centroid, that equal to G, and we have neutral axis. In this case we have area of a solid circular section is pi by 4 multiplied by D square, and we can calculate the average value of a shear stress tau average equal to shear force divided by area. Again, the distribution is a parabolic in the case of all the sections. On the top fiber here, we have shear stress will be equal to 0 because if we consider top fiber, above that there is no area, and at the bottom fiber also there is no area below this. So the shear stress at point A and point B will be equal to 0. Now if you take the y1 value corresponds to the neutral axis, then we get a maximum area. So in this case we have at neutral axis, the shear stress at neutral axis is same as the maximum value of a shear stress, and it can be proved here that this shear stress is 4 by 3 of the average shear stress. So when we have a rectangular section, then the shear stress at a neutral axis is same as equal to the maximum shear stress, and this maximum shear stress is 3 by 2 of tau average. In the case of triangular section, the maximum shear stress will not be at neutral axis. Rather, we have neutral axis shear stress is equal to 4 by 3 of average shear stress, and at a depth equal to d by 2. Suppose I take this depth, then if I consider the bottom area, it is a maximum area. In that case, we have maximum shear at a depth equal to d by 2 from the top fiber, that equal to 3 by 2 times the average shear. And in case of circular section, the maximum area is possible if we take the fiber exactly at neutral axis, that is top and bottom are equal area. So the maximum shear stress is same as the shear stress at neutral axis is equal to 4 by 3 of tau average. So maximum value will be equal to 3 by 2 in the rectangular. Even for triangular section is 3 by 2 of tau average, but neutral axis is 4 by 3 and neutral axis for circular section is 4 by 3. Neutral axis shear stress and the maximum shear stress coincide in the case of circular section. The shear stress at a neutral axis and the maximum shear stress are different location in the case of triangular section. And in the rectangular section, the shear stress at a neutral axis is same as the maximum shear equal to 3 by 2. So number you have to remember 3 by 2, 4 by 3. 3 by 2 is true in the case of rectangular section as well as triangular section, and 4 by 3 second number you have to use for shear stress at a neutral axis. And this 4 by 3 number we can use in the case of circular section, where we have tau at a neutral axis is same as tau max is 4 by 3 of tau average. Now let's consider here we have a solid T section here. T section is consist of one flange and one wave. Here we'll consider the fiber A. The fiber A is the top edge of the top flange. The fiber B has a width equal to B1 as well as fiber A has a width equal to B1. The fiber at C is the top edge of the wave and the fiber at D is the bottom edge of the wave. For this both the top edge of the wedge and the bottom edge of the wedge, we have width is equal to B2. So that is the only difference between the width between the flange and the wave. Tau is equal to V to Q divided by I divided by B. B you have to take the width at that particular section, and the value of Q is given as integral y dA. So to calculate the shear stress at any distance y, first you have to locate the centroid. The area is maximum on the flange side. So let's mark this point equal to the centroid equal to G, and the same axis will be neutral axis. Now as far as A is considered, above the A there is no area, so value of area will be 0. Naturally the y bar will be 0 and the shear stress at point A will be 0, as well as below the D there is no area, and hence the shear stress at point D will be 0. So every time the shear stress on the top fiber and the bottom fiber for all the sections is always equal to 0. So the value of the shear stress at A will be equal to 0, whereas the bottom edge of the wave, the shear stress D will be equal to 0. 2 points we are interested. One is the shear stress at B, one is the shear stress at C, and one is the shear stress at a neutral axis. To find out the shear stress at B, we'll take out this figure separately. So first of all, we'll find out here the shear stress at point B, that is exactly on this fiber. We have to find out the shear stress. So let's mark here this distance is same as equal to y1. If you mark this distance y1, then you have to hatch the area. So this one is the hatch area. This area will be same as b1 multiplied by depth equal to d1. So we have area will be same as equal to breadth B1 multiplied by depth equal to D1. Here we can locate the centroid of the given cross section. So let's represent here this cross section centroid equal to G1, and we have to measure this value of y bar. This value of y bar will be same as equal to y1 plus d1 by 2. So for present section we have y bar is same as equal to y1 plus we have d1 divided by 2. So we know the area, we know the y bar. As far as the moment of inertia I is considered for given section, we have width equal to b1, depth equal to d1. So we have cube of it divided by 12. So correspondingly we can calculate here the shear stress. This value of shear stress will be same as V multiplied by area multiplied by y bar divided by I divided by B. So we have V is the shear force, A is the area, distance is y bar divided by the moment of inertia equal to I, and the corresponding width will be equal to B1. So this one is the shear stress at point B. So the shear stress from A to B will increase parabolically. So we have bottom fiber is B, and this value here is corresponds to the value of tau B, and this value of tau B is given as V into A into y bar divided by I times B1. Now we want to calculate the shear stress here, which one at a section C, and the C is the top edge of the web where we have the width is equal to B2. Now we are interested to calculate the shear stress at the top edge of the wave, that is at C we are interested to know. So for this one we will use the same figure here, because there is hardly a distance between the B and C. There is hardly a hair gap between B and C, one in the flange and one in the wave. So at the top of the we have this section, and this section is same as section CC. For this section our distance is y1 from the neutral axis. It means that area is remain same, y bar is remain same, I is also remain same. Only thing that the value of B will change. So this value of width will be same as equal to the value of B2. That is B2 you have to select. Otherwise everything is remain same. So area is same B1 D1, y bar is same as y1 plus d by 2. That is the same distance of centroid will be equal to y bar from the neutral axis, which is same as equal to d by 2 plus y1. I1 is also remain same, only the width will be changed. Instead of B1 we have to take the width equal to B2. So we can calculate the shear stress at C will be same as equal to V multiplied by A multiplied by y bar divided by I, and this time we have width you have to take at CC, that equal to B2. So basically the B and C, they are on the same straight line. It means that if I extend this line here, I get here the smaller value of the width B2 as compared to B1, and therefore there is a shoot up of the shear stress here. So this value is actually overlap. So I will just show here this arrow from starting with point C. So we have shear stress here is suddenly shoot up, and at this point here we have shear stress equal to tau C, and the value of tau C is more as compared to tau B. So if I take a ratio here of a shear stress at the top edge of the wave, that will be tau C divided by the shear stress at the bottom edge of the flange, that is equal to tau B. So in this case the numerator is remain same, that will get cancelled. This one is B1, so it's a inversely proportional. So we have B1 in the numerator, and for tau C B2 is denominator, so B2 will be denominator. Now B1 by B2 is greater than 1. Width at the flange is more as compared to the width of the wave. Therefore the shear stress at the top edge of the wave tau C is greater than the shear stress at the bottom edge of the top flange, that equal to B. So there is a sudden shoot up. And if you want to calculate the value of tau C with respect to tau B, you have to just take the ratio of their width. After that we have a parabolic distribution here, and the shear stress will be maximum at the neutral axis because the area is maximum. Afterward again you have to draw the remaining one is a rectangular one. So whenever we have rectangular section, then the shear stress will increase, will attain the maximum value, and the shear stress will then go on decreasing and finally we'll attain the value equal to 0. So approximately you will get a distribution like this. So exactly at a neutral axis we have tau Na is same as equal to tau max. And this relation you have to remember the shear stress at B and the shear stress at A. So this value corresponds to the shear stress at B and this value corresponds to the shear stress at C. And the ratio of the shear stress at C to B is same as B1 by B2. So when there is a sudden change in the width, the shear stress will increase. If the width will decrease, the shear stress will increase, and if the width will increase, then the shear stress will decrease. So this one is an important conclusion for us. Whenever we have sudden change in the width from B1 to B, in that case the shear stress will change. If the width will decrease, then the shear stress will increase, and if the width will increase, then the shear stress will decrease. So we can use this concept here for the distribution of a shear stress in the T section and I section. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.